anyway giving his lectures. So thank you so much, Manuel, for the effort. Thank you very much. All right, take your time.
Yeah. You're welcome. Thank you. Okay. So hi, everyone. So I'm going to teach you or tell you a little bit about gamma rays as probes for different things. So for cosmology, axions, and also quantum gravity. The title that I was assigned was fundamental physics, but I thought, okay, fundamental physics includes many things. So I thought I'd break it up a little bit. Yeah, throughout the 3 lectures that I'm going to give you, I will talk about these 3 things. So cosmology, axions, and quantum gravity. Yeah, as Manuel said, I tried to be there, but it didn't work. So for some reason, I was issued a wrong boarding pass. And then when I wanted to board the plane, they told me, no, it's you have the wrong boarding pass. You're not booked on this flight. You were booked on another flight, and that had already left. And then because there was a big strike yesterday in Germany, you can see here this picture I took afterwards at 1:30 a.m. at Frankfurt Airport. Everything was canceled the next day. So no chance to come to Sao Paulo in time. I'm really sorry about that. I would have loved to be there. But I still would like to make this a little bit interactive. So those of you who have a laptop, please go to menti.com and enter this code. Or if you have a phone, it works equally well on the phone. So maybe you could just go to menti.com and then you ask for a code. And this is the code you should enter. So let me just switch screens here. So you see the same thing here. So once people show up, we should be able to see you here. So we have some, interactive things going on here. So menti.com and use this code 17003588. So I give you a second to sign up here. You can react in a way so I know that people are here.
Okay, wait a minute.
Okay, there's one person already. Very good. I don't know how many people are in the room, like 20, 30-ish or so.
Like, I'd say, yeah, 40.
Very good. Excellent. Okay, so I'll switch back and forth between the slides that I'm showing you. Oh, very good. And we have some quizzes, some questions that you can answer. So we have a little bit of interaction also during the lectures, and we break up the lecture a little bit. And we'll do this also in the other 2 lectures. Okay, so this seems to work. Excellent. So let me go back and let's get started. And we come back to Menti later. Okay, so the aim of my 3 lectures is essentially that you people understand this plot, which is really messy, right? So let me walk you through this a little bit. So here we have some kind of gamma ray source, and the gamma ray sources that I will be talking about or that are most important to the things I'm going to tell you are active galactic nuclei or especially blazars. So all the labels that you see here, I hope that this will be covered by Walter and others. But what is important for us at the moment is that these are extragalactic sources that are far away, that emit gamma rays that are, for example, produced in a jet, and then these gamma rays start propagating towards Earth. So what you see here is essentially some distance from the source and the propagation distance. So they start here from the source here and then propagate all the way towards us to the Milky Way. And then at some point we detect them. And I will also not talk about any detection techniques you heard a lot about today, about Fermi, for example, and I believe you heard things about Cherenkov telescopes yesterday. So what can happen to gamma rays during propagation? So one thing that can happen is that they get absorbed, and this is depicted here by this Feynman diagram, which is essentially pair production. 2 photons produce an electron and positron pair. This can be circumvented in so-called Lorentz invariance violating theories of quantum gravity that will be covered in the 3rd lecture. And what can also happen is that gamma rays could convert into axion-like particles. This is shown here in this Feynman diagram. This could happen in the presence of magnetic fields. And this we will start talking about today, and then also cover the next lecture tomorrow. And we will also look at this a little bit more in depth during the tutorials. So I'm not going to cover this, which is essentially upscattering of the electron-positron pairs, which could be used to infer something about the intergalactic magnetic fields, but this will not be covered in these 3 lectures. Okay, so this was just a broad overview of what we're going to cover, and then we can come back to the plot at the end of the 3 lectures, or probably by the end. Yeah, probably by the end of the 3 lectures, and hopefully you have a better understanding about these different processes. Okay, so just repeating myself, lecture 1. So today we'll start off talking about standard model physics, so gamma ray absorption on the so-called extragalactic background light. And then we'll also, in the second part of today, we talk about a motivation for axion-like particles. Lecture 2 tomorrow, we talk about mixing between photons and axion-like particles, and also what is important in that respect are the magnetic fields that are between us and the gamma ray sources, and how we can then actually perform these gamma ray searches. And then depending on how fast we go, how many questions you have, we continue a little bit with the axion searches in the 3rd lecture, and then also talk about the tests for quantum gravity. Okay, so today we start with just basics, gamma ray absorption on photon fields, and we'll talk a little bit more in detail about the extragalactic background light and how we can use gamma rays to constrain the extragalactic background light. And then we switch gear and go to axions. And for that, we first look briefly about what's called parity and charge and parity conservation in the standard model. And we'll talk about the strong CP problem and the axion. And then we'll also look how axions and axion-like particles can actually be the cold dark matter in the universe. Okay, so gamma ray absorption. So you heard this morning from in Ulysses' talk, you heard about Compton scattering or inverse Compton scattering. So where the idea is that you have an electron that scatters on an incoming photon. And in inverse Compton scattering, the energy of the electron is then transferred to the gamma ray or to the outgoing photon. So the outgoing photon has more energy than the incoming photon. And typical Compton scattering is just the other way around, that the outgoing electron has more energy than the incoming electron. So if you turn this Feynman diagram around, you get pair production. So we have 2 incoming photons, and these could then produce an electron and a positron pair. And you can check that this fulfills all conservation laws, and it's also kinematically allowed in the standard model. So this is just a one of the standard QED processes. Okay, so let's have a look at what energies do you need to actually produce an electron and positron pair. So this is sort of our layout. So what we have is an angle theta between the momenta of the incoming photons. And in equations, I will often use this mu, which is just the cosine of this theta angle. And you have the initial photon energies, one that I call capital E and the one that I call epsilon. Usually with capital E, I will refer to the gamma rays, and epsilon will be our background radiation photon. And in order for pair production to occur, you can come up with this threshold condition. So it's essentially beta. I think the square is wrong actually here. So beta in relativistic kinematics is just the 3 momentum of the electron divided by its energy, is given by this expression here. So it's 2 times the masses squared, so mass of electron times mass of positron, divided by the product of the energies and divided by this angular factor. And this just comes out from energy and momentum conservation, okay? And so pair production occurs when beta is, or can occur when this beta is larger than 0. Yeah, so we can make a simple estimate. So if we just take head-on collision, so the photons just go head-on onto each other. That means that the photon or the angle between the momenta is just pi. So they go head-on to each other. This means that mu is -1. So let's plug this in. So this is 1 divided by 1 minus 1. So 1/2 cancels the 2 over here. And then we say, okay, beta has to be larger than 0. And we end up with this simple threshold condition. This will be important later. Okay, so essentially the product of the energies of the incoming photons needs to be larger than the product of the masses of the outgoing particles, which are, of course, the same, being an electron and a positron. Okay, so this is our threshold condition. And this will be especially important in the last lecture when we talk about this Lorentz invariance violating theories. Okay, so let's take a look at the cross-section. So this essentially gives you the probability for an interaction as a function of this beta parameter. The cross-section is now in units of the Thomson cross-section, which is just this number here. And it's called the beta-Heitler cross-section for pair production. Okay, and this cross-section peaks when this beta parameter reaches roughly 0.7. Okay, so if we average the cross-section over this angular dependence, then gamma rays of energy E will pair produce mainly with photons that, with background radiation photons that give an energy so that we're close to this peak here. Okay, so you can actually solve this then and say, okay, this epsilon or background, the energy of the background photon is then this expression here. And if you plug in the numbers, you end up with an energy of roughly 1 electron volt for a gamma ray that has an energy of 1 TeV. Or if you express this in the wavelength of the background radiation field photon, this is roughly 1.2 microns for 1 TeV gamma ray. Okay, so the cross section here peaks for a 1.2 micron photon if you have an incoming 1 TeV gamma ray. Okay, and this will also be important. Yeah. Okay, so what then actually happens, right? So we have our gamma ray source here, an active galactic nucleus or a blazar. Gamma rays propagate towards Earth, and the emitted spectrum will look something like this. Yeah, you heard about this morning, for example. So this is the high or the gamma ray energy spectrum. So you've seen this morning that many of these sources have essentially 2 bumps in their spectra. You can remember this with this camel. So here's your synchrotron emission, and here's your high energy emission. So we're talking about the second bump here for the high energy emission. Okay, but what then will happen is that some of the gamma rays are absorbed in interactions with background radiation fields, produce these electrons and positron pairs, which will of course not reach us. And then the observed spectrum is then essentially this. So you have, instead of the emitted spectrum up here, you have this exponential cutoff. And this exponential cutoff is given by this expression here. So it's an exponential in the optical depth, tau. Yeah, this is what we call the optical depth. And it's a function of the gamma ray energy and the distance to the source. And the distance to the source we usually encode through the redshift, the redshift Z. Okay, so let's talk about background radiation fields. Which background radiation field is actually most important for attenuating gamma rays? And this is our first quiz question. So now we go on to Menti and look at our phones. And then you can actually, let me go full screen here. So now you can actually vote. What do you think? What's the most important background radiation field for gamma ray attenuation? So here you have the plot again. So what do you think? It's a gamma ray. Is it a gamma ray radiation field? Is it X-ray to UV? Is it optical infrared? Is it the CMB? You already see some answers here. So don't get biased by the first answers, right? Just because people are quick. So let's see it. Okay, let me maybe start a timer. 30 seconds. Okay, CMB, people like the CMB. Yeah, of course, that's the brightest radiation field that we see here. Optical to infrared coming up. Yeah, gamma ray background still there. Okay, that looks as if the numbers are pretty stable now. Okay, let's see. What's the correct answer? It is the optical background, optical to infrared. It's not the CMB, and it's also not the gamma ray background, which might be surprising to some of you, but let me explain you why. So 12 of you knew it already. So, if your neighbor had it right, maybe you can quickly turn to your neighbor if you had not the right answer and ask why he or she chose that answer. But let me also tell you. So the reason is, again, what we talked about. It's when you have the maximum of your cross-section. And as you remember from a few slides back, we have the maximum at 1.2 microns for a TeV gamma ray. And 1 micron, this is 1 EV, right? So 1 micron, this is here. Yeah, 1 micron, 10 to the minus 6, this is the optical. So even though the energy density in the CMB is larger than in the optical infrared, the EBL, or this optical infrared background is more important. And the optical to far infrared background is what we call the extragalactic background light, or EBL. Those of you who picked maybe gamma ray background, maybe you thought, okay, 2 gamma ray photons, they have the most energy, so they should be easiest to produce electron-positron pairs. But again, if you look at the cross-section, this is the most important wavelength range here. Okay, so let's have a look at the EBL. So here is a plot of its spectrum. you have wavelengths here, and then you have the intensity in these crazy units. So it's essentially the photon energy, or the energy, the photon energy that we receive per area, per solid angle, per time. And you see this is a very crowded plot. You see, first of all, we have two bumps here. This is an EBL model. And the first bump corresponds to essentially the starlight, all the starlight that has been emitted through the history of the universe, right? And there are many stars that we cannot resolve, but their photons are still out there. So this is the first bump here. And you have the second bump here, and this corresponds to the starlight that has been absorbed by dust in galaxies and then re-emitted in the infrared, right? So starlight heats up the dust in galaxies, and this is also re-emitted, giving rise to the second bump here. We're pretty certain that all the stellar emission should result in these lower points here, which are essentially galaxy number counts. So you point your telescope somewhere, you take a look at how many galaxies are in my field of view here, and from that you can then estimate how many stars are there. So you get sort of an estimate of all the stellar emission that is there. Then there are also these direct measurements, and you see that there is quite a discrepancy between these lower limits and these direct measurements. And the reason is that these direct measurements are extremely difficult to do because we have a lot of foreground emission in our solar system, which is called the zodiacal light. This is essentially starlight, or light from our sun that is absorbed and re-emitted by dust in our solar system in exactly this wavelength range. So probably all these direct measurements of the EBL are affected by the zodiacal light, because the zodiacal light is 10 to 100 times more intense than the EBL. So you have to do a very careful job in subtracting the zodiacal light out of your measurements. So this is very difficult. And this is why this modeling is important. And this is also why it is interesting to look at gamma rays, because with gamma rays, we have sort of an indirect probe of this of the EBL because it gives rise to the absorption. So this is just a more updated plot where all these measurements that are very uncertain are just left out. So you see we have these lower limits, also these, I just want to highlight these cyan or light blue points here, which are from James Webb telescope. So they're pretty new, and James Webb will bring down the uncertainty on these quite a lot. And also I want to point out one point. So where is it now? There's so many here. Sorry. Where is it? Here, NH Lori, this one here. So this is actually a direct measurement from a spacecraft, from the New Horizons spacecraft, which is 50 astronomical units outside or away from Earth. So this has been launched a couple of years ago and has traveled a long distance now. And this is not affected as much or very little by the zodiacal light because it's so far out the solar system. So this is very interesting, and we still see this discrepancy between the star emission, or it's probably due to stars, and what is measured by the spacecraft here. And I'll talk a little bit about the different contributions or what could this be due to here. Okay, so let's take just a little bit of a closer look to the EBL. So I already told you this is usually reported in these crazy new units, nu, which is essentially the specific intensity, as it's called, multiplied by the frequency. And it's actually can easily convert this into the photon density, which are called the NDE, which is just in units of per energy per cubic centimeter. And it's connected through this formula. So it's just E squared times the NDE. It's just 4 pi over C times this intensity here. Here's a numerical factor. Okay, so you can think of this also as a photon density. The EBL is actually the second most intense radiation field in the universe after the CMB. If you integrate just over energy, you end up with roughly 10% of the total energy density of the CMB is in the EBL. If you want to derive the EBL, it's somewhat a scary looking integral. It looks like this. So you have an integral over redshift over what we call the spectral luminosity density. This is this factor over cosmic time. And here's just a change of variables from cosmic time to redshift. Okay, so what is the spectral luminosity density? Oh, sorry. There are just some transformations for redshift that you have to do. Here is the Jacobian for changing integration variables from time to redshift, which is governed by cosmological parameters. H0 is the Hubble constant, and here is omega matter. So the the energy density in matter and the energy density in dark energy. Okay, so what goes into, oh, sorry, this should be an E. What goes into these spectral luminosity densities? So these are the different contributions that I already talked about. So starlight reprocessed by dust. And then I'll talk about a little bit about this later. So possibly AGN and some more exotic contributions. I'll come back to that later. So let's talk about the main contributions, which is starlight and dust. So first, stars. In certain EVL models, you can model this luminosity density through this integral here. So yet another integral. So first off, you have just photons escaping dust absorption. Yeah, so this is just a number, just a fraction of the photons that make it out of the galaxy. And then you have to again integrate over redshift. And what you do here is essentially convolution of the luminosity of a stellar population at some age. Yeah, and this is usually given by stellar or what's called simple stellar population codes. So what is this? This is as a function of wavelength. This is the luminosity you expect from a certain stellar population that is instantly born. Instantly born with some initial mass function. So just some prescription, how many stars you have at what mass. Okay, and usually this is some kind of power law. So you have very few stars that are very massive, and then you have many stars that are less massive. Okay, and then these simple stellar populations evolve with time. So essentially you have young stellar populations up here, and as they evolve, they get less bright, and the peaks are shifted, or the luminosity is shifted towards higher wavelengths. What you also need to assume is the stellar metallicity, so essentially your element abundance once these stellar populations are born. Okay, but this is essentially what is given here. So you have your luminosities that depend on wavelength and on the age of the stellar population. And all of that you convolve then, this is how you compute the age. So yet another integral over redshift. So my head definitely started spinning when I saw this for the first time, many integrals over redshift. But then you have the cosmic star formation rate density. So essentially you convolve this population, these population spectra with how many stars were formed at what time. And here's a collection of observations, or these are not direct observations. Of course, you have to essentially observe galaxies, and from that you deduce how many stars were born over time. And you see that this is given, or here's a fit to this black line here as a function of redshift or look back time in gigayears. So this is the number of stars in units per solar mass per year per cubic megaparsec that have formed over the age of the universe. Yeah, so this can be parameterized with this function. This is a normalization, and these are just some parameters here that fits this quite well. So this is just a phenomenological function, right? There is no physics involved here. It just fits the data essentially. Okay, but if you have all of this, then you plug it into the formula that I have on the slide before. So another integral over redshift, and then you get your EVL from stars. And then you also have, of course, dust. And this is essentially you take your dust spectrum. Then you have to assume something about what the dust actually consists of, for example, some dust grains. Yeah, but for example, some models just assume here a black body. And then you essentially just have the energy that is available from the stars. So this is essentially just the fraction that is of the starlight that is absorbed and can then be irradiated by dust. And then there's a possibility of other contributions. So for example, AGNs can contribute in the UV from the accretion disk, or also from the dust torus. So Walter will definitely tell you more about this. Then there's something called the intrahalo light. So maybe stars have been expelled from their host galaxies and sort of fill the halos around galaxies and also contribute. But models of this usually end up to be, maybe 10% or so of your stellar EVL. But then you could also have something more exotic, like dark matter decay and, for example, axion decay. I will not talk more about this, but I think it's an interesting line of research that had some recent activity. So when you have an axion that decays into 2 photons, you can have this spike here, depending on how strongly these axions couple to photons. And then you can move around this peak here by changing the mass of the axis. Or you could also have stars that are held together by dark matter. You can also have very early stars contribution to this. So there are a number of contributions that could, or one could try to explain, for example, this the difference between the stellar component and this measurement here. Okay, let's check how I do time. Okay. So there are EBL models out there. I already showed you some model curves, and they essentially try to model these spectral luminosity densities and the evolution with redshift. And usually most of the latest models, they agree pretty well on what they predict for the EBL intensity. And usually they're very close to these lower limits from galaxy number counts. So here for redshift 0 are just a collection of a few models that are a couple of years old, but also more recent models look very similar. And here you just see a plot where you have the wavelength here and here a function of redshift. So you see that the EBL then actually decreases with redshift. Okay, so once you have a model or some prediction of your optical depth, of your EBL, you can then actually try to calculate the optical depth. So how strongly gamma rays get attenuated. So gamma rays at energy E and redshift Z0. So here is your EBL photon density. And what you do is a line of sight integral from us to the source. And this is, again, you do a change of variables from your line of sight length to redshift. And then here you have the integral over energy, over the photon density of your EBL. It's decoded here. And then in the end, you just have an integral over the angle of the photon momenta and the cross-section for pair production that I showed you in the beginning. Okay, so you have to have this threefold integral, right? And if you want to also include the integrals over the EBL, then you have like 5 integrals here that you need to calculate. So this can actually be quite time consuming to calculate the optical depth from first principles, so to say. So how does it look like? So here's the optical depth as a function of energy for sources at different distances, so different redshifts. So sources with higher redshift, of course, further away. And you see that, if your source is quite close by, redshift 0.05, then you have, or you start to have strong absorption above 10 TeV, sorry. But if your source is quite far away, at a redshift of 0.5, then you see that we have absorption already at hundreds of GeV. And here's just the same plot, or essentially the log of the attenuation. Function of redshift and of energy. And you see as you increase the redshift or you increase the energy, the optical depth increases. So, and this is, I think, the hyperplane. Yeah, oh, sorry. Yeah. Okay, so how can we then actually try to constrain the EBL with gamma ray observations? So the most basic approach that people have started using somewhat like 10 years ago when we had the first Fermi observations available and a sample of blazars in AGN measured with Cherenkov telescopes, people started using this approach. So you have some model of your intrinsic blazar spectrum that depends on energy and some parameters, and you multiply this with your EBL absorption, which is given by some model, and then you multiply this with an additional normalization that we just call alpha. Okay, so tau was given by a model, and then we just multiply this with this alpha parameter, and then we try to optimize this alpha parameter and see what the best fit is. Some difficulties attached to this. So you have to choose your intrinsic spectrum, right? Because a priori we don't know what the blazar emits. And this could be a straight power law, or the blazar, could have an intrinsic cutoff in its spectrum, right? And then you need to disentangle this intrinsic cutoff from your EBL cutoff. So the way around is that you use many sources for this, right? Because the intrinsic spectrum, there's actually a typo here, sorry about that. The intrinsic spectrum should have cutoffs at different energies that should not depend on the distance, but the EBL cutoff is well defined from these models that it should occur at a certain energy and at a certain distance. So you need to use many sources for this kind of analysis. It depends, of course, on the EBL model, right? So we're putting a model in here. And of course, we can only use sources that have a known redshift. Many, many gamma ray sources in the extragalactic sky actually don't have a redshift because it's very hard to measure it. So we can only use a subset of sources. And as I already said, so we need many sources, best case at different redshifts, because then we have or different redshifts and different energies, so we can actually probe the full EBL spectrum, right? Because if we want sources that are close by, that we measure at tens of TeV, then we probe sort of the far infrared part of the spectrum. Think again about the equation for where the peak of the pair production is. And we want sources that are far away, where we have strong absorption at lower energies, right? So we can probe more of the optical part of the spectrum. Okay, people have done this, of course. So for example, here are some references. This is from Hess observation. So this is the data sets that they used. So they used 1, 2, 3, 4, 5, 6 sources in different states. So you already heard that, or 7 sources. Yeah, but, these blazars can be highly variable. So you want, of course, to have in time a period where at least the spectrum is somewhat stable. Here is the significance with which the sources were detected during this period and the energy range that is probed with these spectra. They tested a number of different models. So simple power law, but then also models with curvature. So log parabola, as it's called here, or power law with exponential cutoff, log parabola with exponential cutoff, or super exponential cutoff. So all these different models you have to test, right? And what they found is then, here is one example. So here's essentially the likelihood. So that Gabi talked about this already. So essentially how well a model is fit as a function of this normalization parameter alpha. And where the likelihood becomes maximal, this is the best fit. And the different lines are for different models. So you see that for this model, a power law gives you a much lower likelihood than models with intrinsic curvature. So for this spectrum, you definitely need intrinsic curvature on top of your EBL absorption. And then they had just a way to then select the spectrum in the end. Basically, they select the spectrum that gives you the highest likelihood. So in this case, this is this green dashed dotted line. So this is a super exponential cutoff with a power law. So this is the green line. And then from this, you get an EBL normalization of maybe 1.2 or so, 1.2 or something. And then as a final result, they had essentially contour on the EBL density, spanning quite a wide wavelength range. So this is essentially the best fit they got, assuming a particular EBL model and then fitting for this normalization. So with CTA, we will probably do something similar. And the nice thing about CTA is that we plan a comprehensive blazar observation program that includes sources that we will monitor for a long time, for which we will get high quality spectra. And also we will follow up flares. So whenever these sources go into high flux states, and hopefully Fermi will be around to inform us that these sources are in high flux states, then we will follow up with CTA. And with this, we should be able to reconstruct the EBL normalization that you see here as a function of redshift. So here we did a lot of simulations of sources, and here's how well we think we can reconstruct this alpha parameter over a wide wavelength range. So this would be then really an enormous improvement compared to what we have done so far with ICTs and Fermi, even taking systematic uncertainties into account. We could also have a more complicated approach by modeling the EBL ingredients directly. So we can just use a model for the EBL and vary its parameters directly. So for example, parameters of the star formation history that I showed you before. And then we can, for each model iteration, we can then compute the attenuation and fit it to gamma ray data. But as I already said, this is computationally intensive and involves numerous integrals. Nevertheless, the Fermi collaboration did this. Using a little bit of a trick in the analysis to save computation time. They used spectra of more than 700 blazars. And with this, they also got this very nice constraint over on the EBL, shown in blue here, also at different redshifts. And also they got constraints on the star formation rate density. So they varied this, and then they got the attenuation, and then they could reconstruct the EBL here. So this is, I think, a very nice way to go forward to actually get some physical constraints out of this, that we can actually say, okay, we can constrain the star formation rate to something like that, and not just vary the normalization of some model, which is not really physical. Okay, so this concludes sort of the first part. Gamma ray absorption. So I told you that high energy gamma rays can produce electron-positron pairs. Cross-section for pair production peaks at energies of roughly 1 electron volt or 1.2 microns for gamma rays at TeV energies, leading to an attenuation above energies for roughly 100 GeV. EBL is the most important radiation field at these energies, and it's mainly produced through starlight and starlight absorbed and re-emitted by dust. And gamma rays actually offer a very powerful tool to constrain the EBL. And we can actually, we start constraining cosmological parameters like the star formation rate. Okay, so how much time do I have left? Like 15 minutes or so?
About
yes, no?
10.
10 minutes. Oh, okay. Okay. Let's see. Then let's just start with a quick introduction of AXION-like particles. And then we'll continue tomorrow. Okay, so let's talk first about transformations in the standard model. So parity transformation. So what is the parity transformation? And I'll try to illustrate this with a cartoon. So parity transformation is simply a mirror transformation. So you mirror everything on this side, okay? So you just have some mirror axis and then you mirror everything. And charge parity transformation is the same thing, parity transformation. But then you also change or you transform every particle to its anti-particle. So that's why I wrote here. As you can see, this is an anti-dog clearly and an anti-cat. So the question I have for you now is parity and charge and parity transformations. Is this conserved in the standard model? So as a little tip, CPT, so where you have charge conjugation, parity transformation, and time reversal. This is conserved in the standard model. But what about these only parity and only charge and parity transformations? So let's go back to Menti here, go full screen. And then what I would like you to do is simply answer yes, no, and if no, which force do you think breaks them? And do you know any experiments that actually have tried to test these symmetries? So just go nuts, whatever you would like to answer, whatever you know, just type it in. Maybe, you know, let's have 1 minute to do this. Okay, you can have also supply multiple answers. Four answers, very nice. Okay, maybe we can start looking at some answers. You can still continue with your answers. So P and CP conserved in the standard model. Yes, 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 yes. No, violated by strong force. This will be interesting. Very good. We'll come back to this. No, weak and strong force. Yes, P, no, CP, yes. I don't remember, sorry. Intuition test, they should be. Very good. Parity, no, weak. Yes, the weak interactions breaks P symmetry. Yeah, Wu experiment. Very good. Very good. Yes, strong force. No, weak interaction. Experiment, pi and decay. Okay, very good. Madame Wu experiment. Yes, very good. I don't know. Yes, that's also definitely fine. That's what you're here for. No, weak force. No. Excellent. Very good. So some very good answers. Okay, so let's get back to our presentations. Excellent. So many of you had the right intuition. No, P and CP are not conserved. And it's especially the weak interaction. So we have beta decay that violates parity. This is exactly the Wu experiment. And for CP, we have, for example, the neutral kaon decay that violates CP. I have some backup slides on this, or if you want, more details, we can you can ask me after the lecture. But I guess you also get the slides so you can take a look. But then, yeah, some of you suggested a strong force. So what about the strong force then? And this is exactly what we call the strong CP problem. So what you can write down is this Lagrangian density that has this theta parameter here. And this is essentially the field tensor of the gluon fields, so the gluons that mediate the strong force. And what this Lagrangian predicts is that the neutron should have an electric dipole moment with a strength that is proportional to this theta parameter, which naively you can just take any value between minus pi and pi. And as this little cartoon should convince you, this or an electric dipole moment violates parity, symmetry, and time reversal. So let's think this is our neutron. And that's, of course, a neutron is electrically neutral. But let's assume you have some charge separation, plus and minus, given rise to this electric dipole moment. And then also you have a magnetic moment mu because we have spin. So what happens under a parity transformation is that the electric dipole moment is flipped, right? And then you just compare these two images and you see they're not the same, so parity is not conserved. For time reversal, what happens is that the magnetic moment or the spin changes sign, and then the magnetic moment is also different. So again, not conserved. So this is a prediction that we should be able to see an electric dipole moment of the neutron. So people have tried to measure this. Here's a function of an upper limit on this neutron electric dipole moment. So you can already see it has not been measured. And here as a function of time, these limits have become better and better. So what we get from the calculation, the prediction is that the dipole moment should have this strength, where E is just the electric charge. Ooh. Now I clicked on the link, so you can go to the paper. But the measurement actually suggests that this dipole moment should be smaller than this number. And this gives you a limit on the theta parameter that should be smaller than 0.8 times 10 to the minus 10. Well, and then you can say, okay, well, this is just what nature decided, right? Theta is just a very small parameter. Or you can say, well, naively, I would expect something to be this theta parameter to be of the order 1. And now it should be smaller than 10 to the minus 10. So I have kind of a fine-tuning problem here that this parameter needs to take exactly the same number. And this number is fine-tuned by 10 orders of magnitude. And of course, especially theorists don't like this. And that's why Peche and Quinn and Weinberg and Bilczek at the end of the 70s came up with this solution. So let's talk about the solution in images. So you have here the strength of the theta parameter and here the neutral dipole moment, right? So the problem is that we live right here, right? So why should this be? And the idea is to introduce this axion. So you promote this theta parameter to be actually a new field that we call A. And this theta parameter is in this new field divided by a new scale, Fa. And what then happens is that if you then incorporate a potential that is generated by QCD, because this then couples to the gluons through this Lagrangian, we get a new particle that acquires mass. And it's essentially a global symmetry that is spontaneously broken. So it's very similar to the Higgs mechanism. So in its potential, this field will relax to its minimum. And this minimum corresponds exactly to the place where the electric dipole moment is 0. And whenever you have a new field that comes about from a new symmetry that is broken, you get a new particle. And this is called the axion. And named after this laundry detergent, which cleans up this mess. And interestingly, for the axion, you have you can actually compute its mass, which is just a function of this additional scale at which this additional symmetry is broken. Yeah, you can also look at this through sort of the Mexican hat potential view. So some time in the very early universe, you had very high temperatures. And then once the temperature cooled down to this new scale, the symmetry was broken. So you have the field relaxes to this new minimum here, which is here. And what can then actually happen, which is interesting, is this interaction with QCD kills this potential. And then this field will start rolling down to its new minimum, where the electric dipole moment is 0. And it will actually then, the field will actually oscillate around this minimum. And as we will see, this is actually, can actually act as cold dark matter. Axion-like particles are very similar. So for the QCD axion, we saw that the mass is related to the breaking scale of this new symmetry. For the axion, the mass and this energy scale are independent parameters. They are, however, predicted in several extensions of the standard model. They come under different names, Myron, Familon. Also in string theory, we have a full axiverse, many axion-like particles predicted there. And here's just some papers that you can Google that give you reviews and tell you more about these extensions.
Hey, Manuel.
However, most generally, they do not solve the strong CPU problem. But we will see tomorrow in the next lecture that we can search for them in a very similar way as we can search for axions.
Manuel, I think it would
Okay, so I think time is up. So
Yeah.
I think I'll leave the discussion why axions and axion-like particles can actually be the dark matter, because it's a little bit different compared to your weakly interacting massive particles. I'll leave this for tomorrow, and I'll stop here, and I'll take questions.
Thank you. Questions? No? See? I guess everybody's hungry.
If someone's talking, I don't hear anything.
So I do have one. So the strongest constraints on axions, they come from astrophysical probes or from direct searches for axion-like particles?
Okay, can I answer that question tomorrow? Because we'll look at the limits for axions and axion-like particles. We'll look at that tomorrow.
Fair enough.
I mean, I could show you. So what I wanted to show, maybe I can. Let me see. Let me just show this one plot that we'll come back to tomorrow. Here we go. So this is sort of the current landscapes of constraints that we'll come back to tomorrow. And it's a combination of many things. So essentially red are laboratory experiments, and green are astrophysical probes. Blue is early universe cosmological probes. And what we'll focus on for gamma ray searches is essentially this corner here.
All right. So any comments or questions? Yeah, you do?
Okay, I have a question, but of the first part on the
Yes.
EVL. Among all the models that are in literature to model the AVL, what do you consider are the best, or at least the ones that can be more helpful to model? I don't know, to constrain the emission from AGNs, or?
Yeah. So what we, I just briefly mentioned this, right? So AGN, we believe that they mostly contribute around 10% to the EBL. So as I said, there are two emission mechanisms that could be interesting. So one is the accretion disk, which radiates in the UV and X-rays, but this will take place somewhere here. But then, of course, this emission is also absorbed in the dust torus that surrounds the accretion disk, and this could re-radiate in the infrared regime, so somewhere here. But just essentially from counting how many AGN we see in the sky, you can make estimates how high this contribution should be, and it should be around 10% or maximum 10% in this infrared regime here.
And I don't know how to say this. Well, are very different the models of the EVL. For example, I don't know, Franceschini, Dominguez, Gilmore, and
So that's a very good question. So essentially, the approaches are different. So one approach is that you essentially take galaxy counts at different wavelengths, and you use that as an input, right? So what I showed you is a little bit of a different approach, that you essentially take these simple stellar population models and then you forward fold them in time, essentially, right? So this is one approach. And then a different approach is that you do not use these simple stellar populations, but essentially you reconstruct this luminosity density at different wavelengths, at different redshift, using essentially galaxy surveys. This is the approach that the models from Alberto Domingos take, and there was a new version of this just 2 years ago by one of the students. So they actually take these galaxy surveys and then reconstruct these luminosity densities directly from these surveys. This is also a very nice approach. You cannot, with these models or with these approaches, it's a bit hard to constrain physical parameters, right? This is interesting for gamma ray absorption. But as you can see here, okay, I didn't include a forward folding model here, but essentially all of the models, they agree very well, at least for Z equal to 0. At higher redshifts, where we have less data, these models show discrepancies.
Okay, thank you.
Ciao Manuel, Franz speaking here. So let's say, for what concerns the stellar population that you can explore indirectly with the ABL models, do you know whether there is someone that is already exploring the first population of stars, like population 3, emitting objects, and how they can be studied through the, let's say, the ABL model?
Yes, yeah, okay. So this has been done sort of like 10 years ago or so, that people looked, okay, how much can these population 3 stars actually contribute? And essentially so these population 3 stars, so these would be the very, very first stars that form in the universe, right? So they should be quite massive and they should be essentially hydrogen burning. And then when they have burned up the hydrogen, then they explode. Okay, they go through, of course, all the evolution, but they should be formed very early in the universe and have these very sort of UV optical spectra, which are then redshifted to the infrared. So you would expect an additional contribution to the EBL here in the infrared. And of course, the hope is that with JWST, we get a better idea of how many of these stars are actually out there to do a better modeling here. But yeah, there were some papers 10 years ago, so using constraints of the EBL that we had back then. Let me see. So for example, with the Hess results, right? You can start constraining the number of population 3 stars. But my feeling is that back then it wasn't greatly constraining the models that we have of the abundances of these stars. But maybe I'm wrong there. But it would definitely make sense now once we have results from James Webb about this, and also, you know, with all the new gamma ray data that we have to revisit also these population 3 stars and also these dark matter powered stars, they actually give very similar contributions.
Okay, thanks.
Further questions, comments? No? So let's thank the speaker again.
Thank you.
And